Good morning. My name is Lisa White, and I'm a software engineer at Twitter, and I work on our real-time streaming products. At Twitter, we process hundreds of millions of tweets per day. If you do the math out, that's thousands of tweets per second, and we process those in real time without ever missing a single tweet. So we built an architecture called PowerTrack. And PowerTrack processes this massive amount of data both quickly and reliably. PowerTrack allows our customers to create a customizable set of tweets so that they can get the tweets that are relevant to them. And the reason that we do this is that for most of our customers, handling the entire Firehose of tweets is a lot to handle. There are a lot of people tweeting publicly at any given moment, and handling all of that in real time would be a lot. So we allow our customers the ability to filter based on the tweets that are important to them so that they can get the percentage of tweets that they care about. So we do all the heavy lifting so that they can get their maybe 1% of the Firehose of tweets that are important to them. So there are a couple of different core use cases that you might have heard about. One would be some research institutions might be looking for data around public health so that they can respond accordingly. There might be different customers that are building different customer service tools. And we also have customers that are looking for signals around natural disasters so that they can respond accordingly. So oftentimes our customers will connect to our APIs, and then they'll deliver their data to their software so that they can do further analysis on the raw data that we deliver. So as a software engineer on the product, I'm excited to share with you the architecture of what we built. OK, so at a high level, the PowerTrack architecture has a couple of different things that we took into consideration with the design. The first is how we filter data at scale. So as I mentioned, we're processing thousands of tweets per second in real time, and so we have to figure out how to make this scale and how to be able to filter in real time. How we ensure data fidelity. So many of our customers are enterprise customers, and dropping tweets on the ground is not OK, so we have to make sure to give them all of the tweets. We have system redundancies, because as you know, in production, it's pretty common, or not pretty common, but it happens that things go wrong, and you can't plan on things being perfect all the time. So we have redundancy in order to ensure that in the case that things go wrong, we have a backup plan. Because we're processing in real time, we have to figure out how to apply customer stream configuration changes. And then lastly, we have multiple data centers, so we have to figure out how to manage the state of our customer applications across these data centers. So at a high level, the input into the product PowerTrack that I work on is the public Firehose, so basically all public tweets that are happening in real time. And ultimately, we deliver data to our customers. And we have a couple layers of our application, the first of which is a filtering layer. So this layer allows customers to have customizable rule sets so that they can filter only on the tweets that are important to them. And then that passes the data along to the streaming layer, which then does some additional processing and also renders the data out to the customer. And so it gets written via HTTP streaming to the customer. And so they have a persistent connection to us. So they'll connect one time, and then they'll stay connected for maybe days or maybe even a week until our next deploy. So they'll reconnect when we do a deploy, or if there's some kind of network blip. But for the most part, they're staying connected all the time, getting the tweets as they happen in real time. And so the customer can manage their rule set that dictates which tweets they get through a REST API. And so this is our rules API. And it allows them to be able to create rules and delete rules. And then this then gets applied to the filtering layer in real time. So the customer doesn't have to reconnect in order to get the updated rule set, which is helpful for them because then they don't have to worry about missing data during the time that they're disconnected. But it does provide a little bit of a challenge for us to figure out how to apply those configuration changes in real time. So the first piece that I'd like to dive into is the filtering layer. And so as I mentioned, we're processing thousands of tweets per second, and that's just our base volume. We also have to be able to handle large events, like a big sporting event like the Super Bowl, where a lot of people are tweeting more than just our base volume. And so we have to figure out how to make this scale. For some customers, like those who are in the financial industry, milliseconds matter, and so we can't deliver the data extremely late. So I'm going to be talking about filtering and how we make that scale to all of our customers and keep up with the real-time volume. Okay, so you might be wondering what I mean by a customizable rule set. So this is a really simple example of a customer rule. So we have a filtering language that our customers use and certain operators that they're allowed to use. So this rule would filter tweets that are from LMW, which is my Twitter handle, and it either has mentions or is a retweet. So it either mentions another user or the tweet itself is a retweet of another tweet. And then there's an implicit and between the from LMW and the next part. And so essentially this tweet would get applied to the customer's rules in real time, and then as tweets come through the Firehose, tweets that match this rule would result in the data that they get. So this is a quick example of two tweets that would match this rule. So the one on the left, you can see that is from me. It's a tweet that I tweeted, and it also has a mention. It mentions another user who's Chuki. So this would match that rule. The one on the right would also match. So when we retweet a tweet, that creates a new tweet. So I retweeted this tweet from Twitter Boulder that's on the right, and because it's both from me and is a retweet, that retweet of the original tweet would go through the Firehose, would go through any stream with this rule as well. So we do this programmatically in real time, and this is an example of the AST, the abstract syntax tree, of how we programmatically would walk through the rule. So this one is pretty simple. So we'd start with the and then we can check whether a tweet is from LMW. Then we can move on to the or, and then traverse through each of the children of the or and check whether it has mentions or is a retweet. And you might notice that there are some optimizations that can be made here. For example, if the tweet is not from LMW, then the whole rule is going to be false. We don't have to continue over to the or and keep traversing through the tree. Similarly, in the or, if we determine that has mentions is true, we can just call the whole or true, and we don't have to keep traversing through the tree. So this is called Boolean short-circuiting, and this is helpful. But it's not that helpful. So as I mentioned, we're processing thousands of tweets per second, and we also have customers that have can have hundreds of thousands of rules. And each of those rules is most likely a lot more complex than this. It can have up to 2,048 characters. And we don't have a limit to the number of clauses that can be in there. So these rules can get pretty complex, and traversing through the entire tree of every single one of our customer rules for every tweet that comes through would be pretty CPU intensive. So we have a mechanism to be able to speed this up, and this is where predicate indexing comes in. So the idea behind predicate indexing is that we are trying to quickly disqualify rules from being matches. And this limits the number of full evaluations, which are the tree walks we just looked at, that we have to do. So the way that we do this is every customer rule is indexed based on the match type of the clauses it contains. So as an example, if someone were looking for the term strange loop, then we would index strange, and then we could also index loop. And so then those two terms would get added into the index, and then any tweet that matches those would then move on to be considered for full evaluation. And I'll go into more detail in a couple slides about how we actually go about choosing what gets in the index, but at its core, what predicate indexing is trying to do is it's trying to weed out rules that wouldn't match anyway. So essentially, we're trying to narrow down our rule set so that we don't have to do a full evaluation on every single rule. OK, so to put this in other words, the rule evaluation is broken down into a two-step process. So when a tweet comes through the Firehose, the first step is to check the index and check whether the rule matches anything whether the tweet matches any of the indices. And then if it does, then that narrows it down to a smaller set of rules for which we put through full evaluation. So as an example, let's say that a customer has 100,000 rules. Then we add each of these rules to the index. And this is most likely more than 100,000 because we have to have every rule in the index, but most rule is going to have more than one thing indexed because we have to make sure that logically, if the rule is going to evaluate to true, the index also evaluates to true. So we'll have more terms in the index. And then when a tweet comes through, we'll evaluate the tweet against the index, and then that will give us a smaller set of rules for which we have to do a full evaluation. So you might be thinking, well, this seems to be overcomplicating it, and you're adding in another step. But actually, because the indexing is so much, checking the index is so much faster than doing the full evaluation, this actually saves a ton of time and saves a lot of CPU usage and speeds things up. And we definitely see that in code when we pick a poor index, and we end up doing a lot more full evaluations than we would see system issues. The index is way faster than the rule evaluation, as I mentioned, so then we can cut down on the time we're spending in CPU. OK, so now you may be wondering what we actually index and how we choose what we index. Well, essentially, we're trying to pick whatever is least likely to occur. And the reason that we're trying to choose whatever is least likely to occur is because we're trying to narrow down the number of full evaluations that we have to do. So if we were to pick something that's highly likely, then we wouldn't be narrowing anything down, and we would end up doing a lot more full evaluations. So in this case, we have a couple of options for what we could index on. So we could index, for an and, you only have to index one side. And that is because either one of those being false results in the and being false. So you only need one of them to guarantee that the index being true results in it being a potential match for the full evaluation. So in this case, we have a choice of indexing on from LMW or indexing on the or clause. But for an or clause, you have to index every term in there, and that's because any one of those being true results in the entire or being true. So for it to actually follow logically that if the index is true, or if the rule is true, the index is also true, then you need to index everything that's in the or. So in this case, we could index has mentions and is retweet. The problem with indexing those two terms is that then when we evaluate a tweet, any tweet that either has a mentions or is a retweet would match the index, which is a lot of tweets that either have mentions or are retweets. So we would end up doing a lot of full evaluations. Alternatively, we can index from LMW. And although I tweet a decent amount, I don't tweet nearly as much as has mentions and is retweet. So by indexing on from LMW only, we'd be able to cut down the amount of full evaluations we have to do by a huge amount, because we'd only have to do full evaluations for the tweets that match from LMW. So in essence, doing this predicate indexing allows us to cut down on the number of full evaluations that we have to do, which are the full tree walks, and that allows us to save a lot of time. So this shows you, if you were following along, that in this case we'd index from LMW. So this helps a lot, and it saves a lot of CPU. However, it's not quite enough. We're still trying to handle all of the rules for all of our customers and keep up with all of this data in real time. So we had to think about other ways to scale our filtering as well. So the next piece that I'm going to talk about is more related to the architecture. So at a high level, again, this is our architecture. The input is the public Firehose of tweets. That is then moved into a filtering layer, where the filtering layer filters for our customers, and then the streaming layer renders that and outputs that via HTTP streaming to the customer. OK, so each of the filter apps, or each of the the filtering layer is broken out into different stacks, where each stack filters for a set of different customers. So in this example, you can see that stack 1 is filtering for customers 1, 2, and 3. Stack 2 is filtering for 4 and 5, et cetera. So this allows us to break our customers out into different stacks so that as our customer base grows, we can simply scale the stacks with our customer base. And we've used this in the past when we've just grown in our number of customers and had to add more stacks. We were able to do that pretty easily. So in addition to that, each of these stacks is processing a full Firehose because they're filtering for a different customer set, and each one wants their full set of tweets that matches. But within each stack, we have a set of apps as well. So in stack 1, in this example, let's say we have 3 apps. So each of those nodes would be reading in 1/3 of the Firehose of tweets. And then each of those would all be filtering for all of the customers, 1, 2, and 3, and then writing the data down to the streaming layer. So by sharing the load, we're allowing ourselves to be able to handle big spikes in tweets and things like that by sharing it across 3 nodes. And the way that we handle this technically is by using a messaging queue. So in Twitter, we use a messaging queue called Event Bus. And this is a Kafka-like messaging queue. So just a quick show of hands. Has anyone used Kafka before? OK, cool. So it's a decent amount of people here. So essentially, each of these stacks would have the same subscriber ID, as you would call it in Kafka. And by using the same identifier, each of the nodes within each stack would be able to share the full copy of the Firehose. And so stacks 1, 2, and 3 would independently keep track of where they're at in the queue so that each one gets its own copy, whereas the nodes within stack 1 all share the same identifier so that they can keep their place together and all share the same Firehose effectively. And so one thing that this allows us to do is as tweet volume changes, we can scale our stacks up and down. Similarly, as we improve filtering in different ways and see different kinds of improvements with our filtering algorithm, then we might need less nodes per stack, so we can have that ability to be able to adjust it. And so we have a dashboard that we use to be able to do this stack management and to be able to control the number of nodes per stack and also how many stacks we have and which customers are assigned, et cetera. So in addition to filtering being very important, data fidelity is also really important to our customers. So as I mentioned earlier, many of our customers are enterprise customers, and data fidelity is extremely important to them. So making sure that we deliver all of the data that matches their rule set. So the way that we do this, again, is along the same lines of using a messaging queue. And in Twitter, that's Event Bus. So as I mentioned, between the Firehose and the filtering layer, we have a messaging queue. And in addition to that allowing us to be able to partition the Firehose, the other advantage is that it allows data to back up. So if there's a big load spike, let's say because of a big event that's happening, then the data would back up into the messaging queue, and the filtering layer would be able to keep processing, and then it would catch up as the load starts to level out. And so it is possible that we might get a little bit behind in the filtering layer, but it's more important that we deliver all of the data than it being like immediate all the time. Although we do consistent load tests to ensure that we're able to keep up with certain levels of volume. But in the case of extreme events, sometimes it is possible that we might get a little bit behind. So we also have a messaging queue between the filtering layer and the streaming layer. And you'll notice here that for each of the 3 customers you see in the diagram connected, each one of those has their own messaging queue. And so what this allows us to do is the filtering layer can publish down to the messaging queue for each of the customers, but the different customers won't affect each other. So if the customer in the middle was backing up, it wouldn't affect customer 3 being able to get their data on time. And the other thing that this allows is if there were to be some sort of network blip or we do a deploy where the customer gets disconnected, they can request backfill. And so what this means is that we take the pointer from where the customer's reading to, and instead of reading from current, we'll go back like a minute or 5 minutes or whatever it is that they specify and just change the pointer in the queue so that they can catch up and read the data that they missed while they were disconnected. So by using this technology and having a queue per customer, we're able to get them kind of out-of-the-box functionality that for us was pretty easy to implement, but provides the customer a lot of safeguards around making sure that they have data fidelity. Okay, so we also use system redundancy to deal with failures. So obviously, it'd be great if things always went perfect in production, but sometimes things go wrong. So we have redundancy in order to deal with those failures. Okay, so I'm going to talk a little bit about the filtering layer. So as we talked about, the filtering layer is broken up into 3 different stacks, which allows us to separate out the customers from each other and also to be able to scale as our customers scale. Each of those stacks has multiple applications, which allows us to be able to increase the number of tweets or change things based on tweet volume. And then on top of that, we have all of this basically replicated. So we have side A and side B, where you can see that for customers 1 through 8, every single one of those customers is both in side A and side B. So we're filtering every single customer twice. And for us, we chose this approach of having 2 different sides because operationally, it makes it really easy to reason about. So we know that we can lose a single node on side A, and none of the customers will be impacted because side B is completely up and healthy. We could actually lose all of side A, and customers would not be impacted. And this is really helpful for things like deploys, because we can deploy side A as long as side B is healthy. Because it does take a bit of time for our applications to come back up once they go down. And the reason for that is because we have to do all of the loading of the rules into the index and do all that pre-processing in order to optimize the rule evaluation. So for us, filtering every customer only once could be problematic if a node were to go down, because then they could get delayed data. But by having 2 sides, we make sure that the customer is being filtered for in real time at least once. And then if one node were to have a problem, then the customer would not be impacted. So our goal here is to limit any kind of customer impact. And then in addition to that, if we do have any kind of operational issue, let's say on side A, and it's 2 a.m. in the middle of the night, we don't have to worry about putting in a change really quickly and messing with things and making a bigger problem in production, because we know that we can kind of take a deep breath and just kind of move on with like a thought-out way of approaching it, because the customer impact is not there. They're not being impacted because side B is healthy. So it also just helps with peace of mind and being able to make sure that we're taking the right approach. Okay. So configuration application. This is how we apply customer configuration in real time. So as we talked about earlier, in addition to the flow of filtering customer data, they also have a REST API where they're able to update their rules in real time. And this is essentially a different product, but it's used for PowerTrack in order to be able to update their rules. And the way that we handle this on the back end is we have 2 different MySQL tables, one for rules and one for rule updates. And just to walk through a simple example of how this would work, let's say they added a rule that was from LMW, and then they decided my tweets were actually pretty boring, so they deleted that. So you can see that the updates table is kind of just keeping a log of what's being updated, while the rules table is actually kind of it's the system of record where we have what the state of their rules is at that time. Then they might decide that they're interested in learning about hiking, and then that they want to get tweets from Jack. So the advantage of us having the data stored in these two different tables is that each filtering application can then subscribe to the updates table so that once it has the rule set loaded, it only has to get updates. And this is helpful because if a customer has 250,000 rules, then if they make a change, we don't want to have to reload all of the rules from the rule table. All we want to do is see what changed. So by the customer subscribing to the updates table, they're able to get changes in real time, and then they can simply just add that rule or remove it without having to reload all the rules. And as I mentioned previously, reloading the rules is a pretty big task because we have to do all that re-indexing of the rules and the optimizations. So reloading the entire rule set is not a super simple task, and it's much easier to simply just apply the updates. But we still keep the rules table completely up to date because that way when a filtering application is restarted, it can simply just reload all of the rules from the existing state. Also for the customers to be able to manage their rules and be able to get all their rules to see what they are so that they can make changes to them, make sure they align with what they have in their system and things like that. So the rules table is the system of record, and then the updates table allows the filtering applications to be able to apply those configuration updates in real time. And then the customer can use this REST API where they're creating and deleting rules where the customer doesn't even have to disconnect. And so they're able to continue getting data while all this is happening in the background. So the way that we handle this behind the scenes is that the filtering applications poll for these updates on a certain interval. So we've explored ways of having the rule updates to be pushed to the filter apps, but in the past, this hasn't been quite as reliable, and we've ended up implementing polling anyway. So we kind of start with polling just so that it can make sure that the data matches what it's supposed to match. But we've talked about in the future having the updates get pushed to the filtering application so that it can get applied a little more quickly. OK. So in addition to applying rule update configurations in real time, we also can apply stream configurations in real time. So we have a dashboard where we can basically see the configuration of the various sides and stacks, and it also allows us to look at monitoring statistics, like what the lag looks like when looking at the subscribing to event bus, whether it's behind for a certain stack, how long things are taking to process, so how much time it's spending on the rule evaluation per stack to see if there's a certain problematic customer. And then based on what we see in that dashboard and based on certain observability or alerts that trigger or things or warnings that we see or things like that, we can use this dashboard to diagnose and then mitigate any kind of customer problems. So one thing that you might have noticed looking at this diagram earlier is that customers 1 through 8 are both inside A and side B, but the configuration of customers 1 through 8 is completely different. So stack 1 on side A is completely different than stack 1 on side B. And this is intentional, and this is to basically reduce our customers being able to impact each other. So each of these customers, we're filtering on rules that they uploaded. And so we try to put all the mechanisms we can in place in order to make them not affect each other. But sometimes there might be things that we miss. So if customer 1 were able to upload a set of rules that ended up to be problematic, or let's say some tweets started coming through the Firehose that all of a sudden matched a ton of their rules just because of some special event that was going on, then it is possible that stack 1 could get a little bit behind in trying to process that data. So on side A, that would impact customers 2 and 3. But on side B, customers 2 and 3 are not on the same stack as customer 1. So customers 2 and 3 would still continue to get their data in real time and not be behind because they're getting that data from side B. And so then we would be able to go into our dashboard once we realize that customer 1 is problematic and decide to take any kind of mitigation. So if we have the option of moving a customer to their own stack, and this is essentially called quarantining them. We have quarantine stacks where they end up on their own infrastructure. So if they have complex rules based on a certain event that's happening, having their own infrastructure gives them the chance to catch up while we might work with support and figure out how to reach out to this customer if their rules need to be changed, if it's a certain problem with their rule, or if we need to make a code change to be able to optimize for this case that was missed. So, and then it also would make the other customers on stack 1 on side A, which would be 2 and 3, no longer be impacted. And so essentially, these stacks would pick up in real time which streams are assigned to them, and then we can make those changes in the dashboard accordingly. And this is helpful for us. So the filter apps, in the same way that they look for rule updates, they also pull an outside application that's kind of managing the state of where what each of these workers should be working on, and then they get back the list of customers that they should be responsible for. So it is possible that we might move things around. We might decide to add additional nodes to stacks if the tweet volume starts increasing, and that's all something that gets applied in real time and is kind of unknown to the filter apps. They're simply just working. So for example, in side A, stack 1, you can see we have 3 filtering applications there. And if we were to decide to add another one, let's say tweet volume increased and we needed more capacity to be able to handle all of the volume, then we could add another one there. So then that one would have 4 filtering applications. And so then instead of each one getting a third of the Firehose, each one would get a fourth of the Firehose. And that's something that we would just get kind of out of the box just because we're using the messaging queue. So each one of those is using the same identifier for stack 1. And so just by adding another node, that would just all of a sudden start getting its portion of the data. In the same way, if a node were to go down, then the ones remaining would kind of pick up the slack, and it would not be affecting of the customers getting their data on time. Okay. So state management refers to how we manage the state of our customers across our different data centers. So back to the system redundancy, we talked about how we have 2 different sides and how that allows redundancy, so if something were to go down on one side, it's not affected on the other. Well, you can basically take that entire diagram and then duplicate it again because we also have multiple data centers. And this is really helpful for us in failure scenarios, but it also is a little bit tricky in terms of managing the state across those data centers. So one particular example of where this becomes a little tricky is customer connections. So when a customer connects to us, they connect with a certain identifier for their stream. And they will have purchased a certain amount of connections. So let's say that a customer purchased 3 connections. That means that they get 3 redundant connections. And that could be because they are bringing the data into their development environment, or it could be because they want redundancy into their system just for extra backup to make sure that no tweets are missed if they were to get disconnected or things like that. And the customer has no knowledge of which data center they're connected to. So that's all done by routers on our side. So the customer connects, and then they could be connected to 2 different data centers. So we have to be able to communicate across those 2 data centers in order to basically make sure that we're not cutting them off of connections they should be having, but that we're also not giving them a crazy amount of connections that would hurt our system. So the way that we chose to do this is using Zookeeper. And the reason that we chose Zookeeper is because when a customer connects, that then requests a lease from Zookeeper for that stream ID. And then Zookeeper just returns back whether a lease is available or not. And so this took a lot of the overhead of writing the code away from us. And one of the advantages of this was that the leases are ephemeral. So unlike if we were to put a record into MySQL or something like that, if a node were to just go down, then the lease would disappear from Zookeeper, and we'd no longer be charging that customer for that connection. Whereas if we were to insert a row into a database, then we would have to figure out some kind of cleanup process to make sure that the customer is actually still connected, and that it's not the case that it just didn't get cleaned up if a node were to go down or something like that. So using Zookeeper, and just because by its nature the leases are ephemeral, that kind of takes a lot of that extra work of figuring out how to make the node's heartbeat and things like that away, and just kind of gets rid of a lot of error, and we're able to use that out-of-the-box technology. So in addition, we're using a cluster that's shared across data centers, so that provides the advantage of it working cross data center. Okay, so for the PowerTrack architecture, what we talked about today was how we filter at scale. So how we basically use predicate indexing and how we have multiple applications per stack to be able to filter data at scale, how we're filtering thousands of tweets per second for our customers, hundreds of thousands of rules. How we ensure data fidelity, so basically how we use event bus, our messaging queue, to be able to back data up into the messaging queue and ensure that data does not get lost along the way to our customers. How we have redundancy of the two different sides to ensure that we're okay in case of any kind of failures. How we apply configuration updates in real time, such as rule updates or where a stream is being filtering from. And then lastly, how we manage the state of our customers across different data centers. So that's the end of my talk, and so thanks for listening, and I'm happy to answer any questions if people have them. Oh, so I think I heard your question was if the two different sides write to the same stream or different streams. Is that correct? So the two sides write to the same stream, and what that allows is the streaming layer essentially can then just read directly from that stream. So you might be wondering, well, doesn't that end up with duplicate data for the customer? One thing that I didn't mention, so thanks for pointing this out, is that one of the things that the streaming layer does is dedupes. So it kind of keeps a rolling window of tweets that it's looked at in the last period of time, and then does deduplication based off of the tweet ID, so that we make sure that they don't get duplicates. But it makes it easier from an operational perspective that it's only reading from one stream rather than have to coordinate multiple. Sure. So the question was, do we have any guarantees around fidelity or order? And so around fidelity, in the case that we were to miss any tweets, that would be considered like a system outage that we would work with support to post and communicate to customers. So I'm not sure about like formal SLAs, but we do consider it a production issue if there were to be a case where data were to be missing. And that's why we have so many things in place like the redundancy in multiple data centers, and we have the messages in the queue in order to ensure fidelity. Another piece related to that is the filtering application doesn't actually acknowledge that it read and processed the event until it processes out to the rendering layer. So it makes sure that the data has actually been written out. And same thing with the rendering layer, it doesn't acknowledge that it actually read the data until it writes that out to the customer stream. So this makes sure that we don't lose data if a node were to go down even, because then another node would pick it up because it's never actually been acknowledged. And then the next part of your question, can you remind me what that was?
The order of the...
Oh, yeah. Yeah, so the order is not guaranteed. So it's basically producing the tweets in real time as quickly as we can get them out. Yeah, okay, so the question was, how do we deal with production issues? It seems like because the system is pretty complicated that it would be difficult to kind of nail down where the issue was. And I think because we have it broken down into multiple different applications, it's pretty easy for us to see where we've seen issues. So we'll have error counters and have that in our monitoring dashboard, so we'll know if we ever weren't able to publish an event. And so, I mean, for the most part, we get notified of issues in our system before a customer would even notice, or a lot of the time a customer doesn't even ever get affected because it only happens on one side and not the other side, and so it's not actually even customer impacting. So for the most part, based on what the issue is, we're able to kind of narrow it down just because we have things broken down into discrete applications that we monitor separately and all have different jobs that they're responsible for. We also have a QE team that is constantly streaming data, and they're making sure that we're not missing data from the Firehose. So this is really helpful for us so that we can make sure that this is running in our staging environment happily before we ever push that to production. So that definitely helps with just kind of peace of mind and making sure that things are fine and we're not pushing those kinds of bugs to production that would result in data loss. So I think that we're out of time, but I'm happy to stick around, and I'll be around for the rest of the conference. So if anyone has any additional questions, I'm happy to talk about it. So thank you.